All right, let's see. We did not have a homework assignment in here, correct?
Correct.
Okay, so let's keep going and try to power through the rest of our Boolean, or our, I'm sorry, our Python to Java conversion stuff so we can get into actually writing some Java things and pushing forward with the content. So we're going to go ahead and introduce arrays. So arrays are like lists in Python. When we arrays also follow something called contiguous memory. So let me actually show you the line first. So if I come over here to Eclipse, and I am going to go ahead and gut this. I don't remember if I put any of the code up on Slack yet. Create a, I'll give you a lot of options there, don't you? Are any of them the ones I wanted? Is this a code snippet? This is a code snippet. There we go. Or is it just under text snippet? Yeah, that's right. All right, so there's some code that we've been working on in class, so I can gut this a little bit. So that shows you things with creating variables, strings. We started working with strings a little bit, conditionals, Boolean expressions. Last time we looked at the bitwise operators, even though I've kind of mentioned that that's not something you're going to commonly use. It's not something I'm going to test you on in here, but you will likely see it in the 325 class that a lot of you are in right now, because that's a pretty common thing to do bit shifts right and left and do bitwise ands and ors and XORs and all that stuff. So I mostly showed that to you from the perspective of if you ever write it and it doesn't give you an error, but instead gives you this random number, there's a reason behind it. Okay, so let's go ahead and let me just gut main here. So if we want to create, we're effectively creating the same thing as we did in Python, a list in Python. We would have said something like list is equal to something like that, right? And this gives us a collection of, an empty collection of elements. Again, Python is a loosely typed language, so we don't get to say this is the kind of thing it's built for holding. All right. Lists in Python do not necessarily use contiguous memory. What do I mean by contiguous memory? Like I say it in this previous thing, right? So arrays are fast in languages like C, C++, and Java because they use contiguous memory. Contiguous memory is a fancy way of saying memory that is right next to each other. And so, we'll talk more about this here in a few minutes. Okay. Now, when you get into the 300 class, we start talking about implementing linear and nonlinear linked data structures. And one of the things we do in there is we create something called a linked list, which is effectively a list from Python, where a list can start off with nothing in it, and then you can just start arbitrarily adding things to it. And if you, we just look at, well, here, let's go this route. So if I want to create a collection of integers in Java, I would say integer array So the type of thing I'm making is a array capable of holding ints. And I'll go ahead and name it AR. And I'm going to say that guy is equal to, there's the new keyword, int array 10. Okay, what this line says is create new memory that can store 10 integers right next to each other. All right, this is contiguous memory. Let's see. I'm going to write this a little bit. I'm going to put it above it. I.e. contiguous memory. Okay. Right now, this array is empty. It is a container ready to hold stuff. All right, if I want to start putting things in there, I could write a loop real quick and fill it up with the numbers 1 through 10 or something like that. I can say for int I is equal to 0, I is less than ar.length, I plus plus. There's something going on with my autocomplete in Eclipse. I saw that last time and I didn't fix it yet. And then I'll say AR at bucket I is equal to, let's say I. So that'll fill it up with bucket 0 will have a 0, bucket 1 will have a 1, bucket 2 will have a 2, so on and so forth. All right. Now, if I come out here and I do system.out.println AR, what do you suspect will display to the screen? If I was in Python and I created a list and filled it up with 0 through 9, and then I said print the name of the list, what would print to the screen? Yeah, the contents of the list, right? I'd see 0 to 9 to the screen. So as a Python programmer making a transition to Java, we might suspect this is going to do the same thing, right? But it won't. This is going to give us a memory addressy looking thing. All right, and then you can actually see evidence that this is actually a memory address within the Java virtual machine. So the Java virtual machine is a computer built out of software, so it manages its own internal memory. So the actual memory address is this hexadecimal value here. But notice that before we have an @ symbol here, and this is an integer array at this fake memory address inside of the Java virtual machine. It's not really a fake address. It's just the Java virtual machine has its own collection of software-based memory, which then maps to real memory on your computer. So they're keeping track of this number. We don't care about this number necessarily. It's just, when we look at this, it looks like crazy memory address thingy. Okay? So punchline is that AR holds a value. The value it holds is a memory address. Memory addresses, the variable type that we think of for memory addresses is something called a pointer. All right, I'm going to put this on a slide right before this. So if I say int array AR is equal to new int array 10, like that. AR is a variable that holds a memory address which points to the beginning of the array in memory. This address came from the new keyword, which acts as our real estate agent and gives us a place in memory capable of holding 10 contiguous ints in this case. how much memory is needed in a row? Let's say how much contiguous memory is needed to hold this array. How big is an integer?
I'd say a byte.
1 byte?
Yeah.
Okay. If it was a byte, so remember we looked at that chart and showed all our primitive types? And that was in the same one we talked about the Y2K problem. So why do we have so many different ways of holding unsigned or holding signed integers? We had bytes and shorts and ints and longs, right? So an int is one of those guys. Now a byte can hold, is 8 bits, is a byte. So it can hold -128 to +127, only 256 unique numbers. A short, which is 16 bits, can hold 65,535 or 536 unique numbers, ranging from -32,768 to +32,767. And everybody should memorize all these numbers, right? You don't have to memorize the numbers. You can calculate them pretty quickly by saying roughly ±2 to the 7th power, ±2 to the 15th power, ±2 to the 31st power for integers. So integers are 32-bit values or 4-byte values. A byte is 8 bits. 8 times 4 is 32. Okay, so an int is a 4-byte value or a 32-bit value. It can hold 4.2 billion unique values, so roughly -2.1 billion to +2.1 billion. So if I say 2 to the 31st power, there's your, so it's -2,147,483,648 to +2,147,483,647. That's the range of values that will fit inside of an int. All right. From a programmer's perspective, what do we really need to know? What I'm doing here is I'm melding 2 classes together. So in that computer architecture class, the 325 class, it's super important that you know the range of values that a certain number of bits can represent. If you're looking at a processor, a computer processor, and you have a hardware register that can hold 16-bit values, there's a limitation to the maximum size of the value that you can represent in that hardware register. You can represent a signed 15-bit number, because you have to encode it to hold the positive and negative value, or you can hold an unsigned 16-bit value, which only is going to get you to 65,535 as your maximum value. Right? These are important concepts when you're actually talking about what's under the hood at the hardware. As a computer programmer, we more want to have like a ballparky idea. You know, bytes can hold kind of a smaller chunk of, you know, the values it can hold are small. Then a short, which we hardly ever use, can hold kind of bigger values. An int can hold even bigger values. A long can hold even bigger values. And if we run out of that, well, let's put it there. We must have something else on the object side. Java has this thing called big integer that can just hold arbitrary size values. Okay. Now, a funny thing is when we go back to those primitive types, one of the things that that was that whole conversation about the Y2K bug. Why do we have so many different ways of holding signed integers? It's because memory used to be super expensive. So a programmer in the 1970s would have had to be very, like this conversation we're having right now would need to be very precise. These numbers that I'm throwing out there would have been super important, right? Because if you were writing a program and you only needed to hold the numbers 1 through 10, maybe you're writing a loop that did something, whatever, you would want to choose the byte primitive type to hold that, because you want to use the minimum amount of memory possible for holding that value, because you didn't have that much memory to begin with, and memory was really, really expensive. So you, as a programmer, you needed to be careful about the mess you made inside the computer's memory, right? Today, memory is dirt cheap and we have a ton of it. That doesn't mean there aren't some applications where we do need to care about memory to a certain extent. For example, let's say you're a video game writer, okay? And you are writing games specifically for PlayStation 4, PlayStation 5, whatever it is. Those computers, even though they do have a lot of memory in them and stuff like that, they have a finite amount of memory in them. So any game you write, you know you have to make it work well on that specific collection of hardware. The processors on there, the memory that's in there, all that stuff. That's your limitation, the constraints of your game. You can make the greatest, coolest game in the world, but if it doesn't run well on the device, people aren't going to like it, right? All right, so it's not that these things are not important to programmers at all today. It has more to do with it's not necessarily on our radar most of the time. All right, so as general business application developers, call it 99% of the time, we just use integers, an int, to hold all of our signed whole numbers, which is kind of funny in that we do have another option past int. We have a long, which is plus or minus 2 to the 63rd power. It's a 64-bit value, which is it's like 9 point some quintillion or something like that. 2 to the 63rd. 9.2. I'm pretty sure that's quintillion, which is trillion, quadrillion, quintillion. Big number, big number, but not infinity. So it might be possible that you need to hold even bigger values, okay? So I might question why modern programmers don't just use longs for everything. If we don't care about memory, you have plenty of memories, well, we're certainly not going to hit 9.1 quintillion. I mean, 2.1 billion like feels possible, right? Not probable, but possible. You might have a program that counts into the billions, but quintillions, I mean, that feels made up. We're probably not going to have a number like that, but historical trend, modern programmers use ints to hold their whole signed numbers. They use doubles for their floating point numbers, and double, we have two different ways of doing floating point numbers. We have floats and we have doubles, and doubles are kind of like longs. They're the bigger of the two. So a double in Java is 64 bits before the decimal point and 32 bits after the decimal point. A float is 32 bits before the decimal point, 16 bits after the decimal point. Okay, so in any case, answering this question here for us as programmers who are also computer scientists, how much contiguous memory do we need to hold this array? If we have 10 integers and an integer is 4 bytes, we're going to need 40 bytes of memory. Okay, or we can say we're going to need 320 bits of memory. And int is 32 bits. We need 10 of them. 10 times 32 is 320. These are the same value, right? 40 bytes and 320 bits. Those are equivalent ways of saying the same value. Okay, so this new keyword, I've kind of advertised this as being like our real estate agent. We're saying, I need you to go and talk to the Mac OS, talk to Windows, talk to Linux, whatever OS we're running on, go and talk to that operating system. Really, the new keyword in Java is talking to the Java virtual machine, which then is talking to the operating system. But go and talk to the operating system and find me a plot of land that's big enough to build a house on that's 40 bytes big, okay? Because if we're building a house in real life and you're building one of these giant mansions, you can't just find 7 or 8 plots of land that might be somewhere in the maybe the same zip code. You kind of want the whole house right next to each other, right? You want the whole place right there. Arrays work that way. I'm asking for a chunk of memory that I can put my entire array in. So going back over here, this memory address What that guy is it is what's called the base address of that land, of that memory. So we're going to say the new keyword returns the base address, that is the very beginning of the memory it reserved for you. So that's what it gives us, is that base address. So back here in Eclipse, when I printed out AR is a variable. Variables hold values. A variable always resolves to its value. So I'm saying print whatever the value that lives in AR is. And what it printed out here was a memory address. So that proves what I'm saying to you out loud is right here, the new keyword went and found enough memory to store this many of these guys in a row. And it returned that value into my variable AR. So AR holds that place in memory, okay? Now, if I were to, on the very next line, if I do something like system.out.println, AR at bucket 3. Now remember, we, in this loop right here, we went through and we filled up AR with all the numbers. So AR at bucket 0 is a 0, AR at bucket 1 is a 1, AR at bucket 2 is a 2, so on and so forth, okay? So that's what we put into that array. So now if I print out AR at bucket 3, what it's going to do is it's going to actually give me the value that lives at bucket 3, which should be the number 3. That's what we put in there, right? If we want to make things a little bit more interesting, we can say multiply it by 2. So then it'll give us a 6, right? It'll be a 0, then a 2, then a 4, then so on and so forth. All right, so that way the numbers won't match identically. So if I go ahead and run this, there's our 6. A 6 lives at bucket 3 in variable AR. Now, what's actually happening here? This is saying, go to memory address AR and take 3 int-sized steps and give me I'll do this as a multi-line comment just so I can and give me the value you found there. That's what AR at bucket 3 says. It says go to the memory address where AR is, the base address, and then walk forward 3 integer size steps. An integer is a 32-bit size step, a 4-byte size step. So I will walk through memory. I'll take 1 step, 4 bytes, another step, 4 bytes, another step, 4 bytes. Then I'll look down at the ground and I'll say, what did I find here? We found a 6. Okay, so let's look at a picture that shows that. When we say int array AR, in this case, I'm only creating one of size 5, so when my picture wasn't too big. All right, this new keyword is our real estate agent. It's going to go and get some memory for us, right? That memory gets returned into this variable AR. Now, to make life easy for us, I went ahead and pretended like the memory address it gave us was 100. Because that's an easy number for humans to work with. This number is less friendly. Okay, so we're going to assume it gave us memory address 100. So that is the base address of this array. Notice that bucket 0 of this array lives at memory address 100. Now, if I'm operating off of, well, here I put values in here, but in our thing, we had a 0, we had a 2, 4, 6, 8. That's the values we stored in ours from our example code. Make sense? All right, so let's say we have some value. So if I say AR at bucket 3. What I do is I start off at memory address 100. I go into memory to the base address. Then I take 1, 2, 3 hops through memory of size integer steps, which brings me to memory address 112. If integers are 4 bytes big, I start off at 100. The next int will start at 104. So the first int will be stored in memory address 100, 101, 102, and 103. 4 bytes. We have 32 bits of memory that are going to be used to store that integer, that single integer. The next integer starts at 104. The next one at 108. The next one starts at 112. So my value 6 here will be a 32-bit representation covering memory addresses 112, 113, 114, 115. Now a 6 is, what's the binary version of the number 6? So if I were to say, this very next screen, what is 6 in binary? Remember, my exams always have conversion questions on them. So if I want to take the decimal value 6 and convert it to binary, what is that value? 110?
I was going to say 0110, but that first 0 could be eliminated, right?
Well, we're going to have a lot more zeros than that when we have to represent this thing as 32 bits. So what's our pattern for this? We take 6, we divide it by 2. 2 goes into 6 3 times. Zero remainder. 3 divided by 2. 2 goes into 3 1 time with a remainder of 1. 1 divided by 2. 2 goes into 1 0 times with a remainder of 1. So we read our answer from bottom up, so it's 1 1 0. This is the 4's place, the 2's place, the 1's place. 4 plus 2 is 6. All right, so that's the decimal number 6. What is 6 in 32-bit binary? That is 1, 2, 3, 4, 5, 6, 7, 8. It's that. That is the 32-bit representation of the binary number 6. I have 32 zeros and ones in total, most of which I'm wasting here, right? Because I'm holding such a small value. Now, again, this is more of a 325 concept. So hopefully this will benefit you over in that class, but this is what's actually happening under the hood. I have my computer memory, and if I'm going to have 10 integers, that means I'm going to have 10 times this number of zeros and ones in memory next to each other. So I'll have 320 bits of memory, and I walk through it 32 bits at a time. And each one of those 32-bit hops stores an integer, some value between negative 2.1 billion and positive 2.1 billion. In this case, it's a very uninteresting number 6, right? It's almost all zeros with leading zeros there. So this is 0 in the 1's place, 1 in the 2's place, 1 in the 4's place, 0 in the 8's, 0 in the 16, 0 in the 32, 0 in the 64, 0 in the 128, blah, 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 blah. All right. So if I say go to AR at bucket 3, I go to the base address and then I take 3 steps to get to that thing. And then I say, what is the value I found there? Does that make sense? This is why arrays are fast. Computer memory is fast, right? One of the things you're going to be talking about in 325 is the different kinds of memory speeds. You know, have you already talked about hardware registers at all in that class? What have you talked about so far? Oh, something, I assume.
325, you mean?
What's this?
In 325?
Yep.
I mean, we really haven't gotten into much. It's been like a lot of seat charting and getting to know each other, but we're just now getting into, I guess, the beginning of the class, it seems like.
Okay. Well, you'll be ahead of the game with this stuff. Hopefully you talk about hardware registers and processors before too long. All right. MIPS. Yeah, you're going to be doing MIPS assembly in there? Yeah, I'm sure.
MIPS.
Yep. MIPS. It's an old RISC architecture CPU type. Yeah. So in any case, that's how arrays work. And the reason why they're so fast is I can get the value at a particular place in memory by calculating what bucket it's in. Okay, you can almost think of this like memory works you know how the addresses in real life are kind of complex, right? We don't see them as being complex because we're used to addresses in the real world. You have like a number, you have a street you live on, you have a city you live in, it's a state where the city exists. So when somebody gives you 123 Elm Street, Wisconsin, Fond du Lac, Wisconsin, something like that, then they give you a zip code or whatever, that gives you a lot of information about where to find that place in the world, on the planet Earth, right? Okay, so that's a pretty complex memory address, so to speak. Our memory addresses here are far less interesting. It's just a house number. All the houses live in this one gigantic street. Go to house 3 billion, and you'll find what you're looking for. Okay, and you just walk down the street. Well, with computers, we can kind of teleport down the street. So I can start at the beginning of the street and then just take a big old hop all the way down to where I need to go. Fast. We're using the actual memory hardware to get to the place in memory where we're trying to go. Make sense? So we think of arrays as being quick, as opposed to lists in Python or linked lists that we'll talk about next semester, where each thing lives somewhere in memory, and in order to get to thing 4, you have to first go to thing 0, then hop to thing 1, then hop to thing 2, then hop to thing 3, so on and so forth. And those things don't necessarily live next to each other in memory. So what's the advantage? The advantage is I can have collections that can grow and shrink arbitrarily at the cost of speed, because I can't just go right next to each other to get to elements. I have to jump all over memory potentially to get to stuff. All right.
So a list in Python like arbitrarily places a value in memory?
Correct. Lists in Python, I guess I'm not necessarily 100% positive how they're implemented under the hood, but I would suspect they are implemented like linked lists. Because if they're not, well, let me show you this example here. Let's say that for AR, I'm currently storing 10 elements here. What if I want to store an 11th element in AR? Well, in Python, I just append an 11th element, right? No problem. Not in Java. If I try to say AR at bucket 10, which would be the 11th bucket, bucket 0 through bucket 10, if there was 11 elements, and let's just say I try to put a 5 in there, and I go to run this, it's going to scream at me. Array index out of bounds exception. It says, look, pal, you asked me for 320 bits of memory. You told me right there, you're going to hold 10 values. Yet right now you're trying to access bucket 10, which is the 11th value. Not allowed. You know, this is like asking your real estate agent to go find you a plot of land that can hold 4 acres, and you try to build on 5 acres. You didn't buy enough property. Make sense? All right. So, I mean, in real life, what can you do? you can maybe buy the land next door if it's available. Okay, maybe in a computer you'd luck out and it would just so happen that the land next door, the memory address next door, happens to be available, and maybe that's what the operating system will give you next, but there's no guarantee of that. All right, so really, if I want to hold something in bucket 10, I have to change the value of AR and say AR is now an integer array that can hold 11 things. Now, by doing that, I can now legally do what I just wanted to do there. All right, but if I go to print out AR at bucket 3, I get the default value in that array of a 0. Because my bucket 3 here and the bucket 3 here are not the same places in memory. The new keyword always gets us new memory. So up here, when I built my array, I got a base address for some place in memory that can hold 10 integers next to each other. Down here, I decided, oh, I want to hold an 11th value. So I went ahead and I knocked down the old house. Well, actually, I didn't even knock it down. I just abandoned it, right? I just left all those values I had loaded into memory somewhere. And I just said, look, I'm forgetting about that. I no longer have a way of accessing it. And I'm going to ask for new memory capable of holding 11 things. And I'm only going to put something in bucket 10. So the thing that we used to think we put in bucket 3 and then printed it out still exists in memory somewhere, just for a moment. But we have no way of getting there, right? We have something called a pointer count. So AR points to a place in memory. But once we redefined AR, it now points to a new place in memory. That old place, we've lost access to it. All right. And then so Java has something called automatic garbage collection, where think of it like a dump truck that's going back and forth through memory looking for places in memory that no longer have things that point at them. And what it can do then is it can let the operating system know that this memory is no longer being used. You can hand it out to somebody else if they are looking for some land. Make sense? So we abandoned the original AR. Notice we have this memory address here. I'm going to go ahead and I'll print out AR again the second time, and you'll see they're different numbers. This value and this value are different values. I asked for new memory. That makes sense? Now, I could go ahead and copy everything over. So I could actually say int array AR2 is equal to a new int array 11. And then I can say for int I is equal to 0, I is less than AR.length, I plus plus, AR2 is AR2 at bucket I is equal to AR at bucket I. So that'll go through and it'll copy buckets 0 through 9 from AR into AR2. Okay, I'll get my original values. Then I'll set AR2 at bucket 10 to 5. Adding my 11th value. If we're trying to keep it consistent, this would be 22, 11 times 2. Okay. So we'll put an 11th value into my AR2. So now AR still points to its original place where there's 10 values. AR2 points to a different place in memory that now has 11 values, the first 10 of which have been copied over from AR. And now what I ultimately want to have happen is I want to abandon this memory where AR points to and have it point to the same place as AR2. AR is equal to AR2. AR is a variable which holds a memory address. It used to hold the memory address that pointed to the original place where AR lived in memory. Now it holds the memory address that is the same place that AR2 points to in memory. So now they both point to the same place in memory. That makes some sense? So now if I were to print out AR and AR2, you'll see that they're the same number. And this guy has been abandoned. We've left that memory address behind. And the automatic garbage collection is going to go sweep it up. Okay. We spilled it up, spilled over there, and now we're going to go and do something else. So that means now, if I were to print out AR at bucket 3, we would still get our 6. If I were to print out AR at bucket 10, we'd get our 22. Because AR now points to my brand new array. But I had to create a separate array first. That's why we created AR2 first, a new place in memory, copied all of the old values over, added my one additional value, and then made the old array point at the same place in memory as the new array points to. Make sense? Now, the real life example of this would be, let's say you buy a house and then you want to add on a deck. Okay. Now, usually in real life, presumably you have enough space. Let's just say your land is enough to hold the deck. In real life, what do? We hire somebody and we add an addition, right? You pay them some money and they tack something on to your house. In the computer world, if you want a deck, what you instead do is you buy a new plot of land, build your old identical house on that plot of land, add the deck to it. The plot of land needs to be a little bit bigger, and then you just abandon your old house. That's expensive, right? That doesn't seem as efficient as just building a deck onto your actual house. Although sometimes in real life, it is cheaper to just buy a different house that has a deck than it is to add a deck, but whatever. So this is one of those examples where we have to change our mindset from real life to computers. We would never be that wasteful in real life, correct? In real life, we would never say, I'm going to literally buy a second house and put a deck in it and go live over there and just leave this one behind. There's probably some billionaires in the world that might just do that. It's like, yeah, the pool wasn't big enough. So, we bought a new house in Malibu with a bigger pool, and I might get around to selling it, but I want to keep it, stay close to the kids. Something like that. But generally speaking, we wouldn't do this type of thing. All right. So at this point, we are, pun intended, talking about pointers, right? Lots of memory pointers, things like that. So are we relatively comfortable with that concept right now? What I really want us to get out of today's lecture is that the new keyword gives us a place in memory, and arrays are stored in contiguous memory. Now, that is super important as a computer scientist. In a language like Java, memory is managed for us. So I might put into a slide a truth. In older languages, the programmer is in charge of managing memory. We create new memory. We delete memory when we no longer need it. And directly manipulate memory. So, for example, in a language like, let's say C, the C programming language, I can do something like int pointer AR is equal to malloc 10 times, I'm going to write this in a fairly old way. Technically, the current version of malloc doesn't require you to do the size of thing. 10 times size of int. All right, so this is asking for 10 times whatever size an integer is, which I've advertised as being 32 bits in Java. So this will get me my 320 bits of memory, or my 40 bytes of memory. And ultimately, AR will hold that base address. So malloc in C is like the new keyword. Let's say malloc equal new keyword. Now, what you can do though in C is you can do something like this. The value at AR plus 3 is equal to 7. I can directly walk memory. So this says, take AR, which is the base address, add 3 steps to it, 3 bytes to it, or 3 4-byte chunks to it, and then give me the value that lives there and store a 7 in that place. Okay, so I'm going to write it like this. I'm going to say that, and then I'm going to do something like printf set the value AR plus 3. That type of thing. And I'm going to put an ampersand before this guy. So at this memory address, store a 7. Go to this memory address and give me the value that you found there. What's the punchline of this in an older language like C? C has a specific syntax for working with memory. Java does not. Something you'll find in a lot of textbooks with Java is they'll say pointers don't exist in Java. What's a pointer? A pointer is a memory address. It's a variable for holding a memory address. Okay? If it doesn't exist, I didn't write a very long program to find 3 of them, right? Pointers exist in Java. What we don't have in Java is a specific syntax for working with pointers. They've taken that away from us because Java manages memory for us through automatic garbage collection and things like that. They would say that it's safer for the programmer to not make mistakes. And generally speaking, and we'll have examples, we'll bump into this. Generally speaking, there's a correct way to manage memory, and only if you're trying to do something either very weird that might be necessary or very bad, a la virus writers or something like that, might you be interested in directly manipulating memory. All right, questions about any of the stuff we talked about today? All right, so no homework for Friday, but there is a risk of a in-class quiz on Friday over the pointer stuff we talked about today. So study today's lecture. I would probably do it on Blackboard or in person in class, depending on if I, because we do have people online. So if you're in class and you have your laptop and you want to do it on Blackboard, you can. Otherwise, you can take out a piece of paper and just submit it. All right, I'll see everybody on Friday. If you need to represent values bigger than 4 bytes, Ben, you would use a long, which is 8 bytes.